So for the last kind of topic that we're going to talk about in this unit, we're going to talk about representing functions as power series. So we've said we can approximate any function with a power series. We've also said if it's an infinite Taylor or polynomial series, it perfectly matches. And so we're going to play with how this is actually useful for us. So for a power series, recall that the Taylor series approximates the function as an infinite polynomial. And in this case, it's not really an approximation. It exactly represents the function. Now, because the series is a sum of terms, then algebraic and calculus operations can be performed. So for example, addition, multiplication, derivatives, integrals, etc. So in other words, if I have something like f of x is equal to a0 x minus a to the 0 plus a1 x minus a to the 1, etc., etc. Then if I multiply, say, the function on the left by 3, I can also multiply each of these terms by 3. If I take the derivative of the function on the left, then I can also take the derivative of each of these. If I integrate the function on the left, I can also integrate each of these terms. And depending on what the general term is, so a sub n, I might be able to even operate on the general term and rewrite the entire function, rewrite a specific power series for a given unknown function. And this is where we mainly use it in the AP test, is taking one function with one power series and transforming it into another. So those algebraic calculus operations allow us to manipulate a known series to find an unknown but related series. That's what I just said there. We can take a function where they give us the power series, or it's easy to calculate the power series, and then we can calculate a related power series. So we're going to do two examples here. The first is given g of x, find the power series for f of x. So g of x is 1 over 1 plus x squared, and they're telling us this is our general expression. So now we need to find out a relationship between how g of x and f of x are related. Because if I know how g of x and f of x are related, that's also going to be how their series are related. So looking at this, it may not be immediately obvious to you, but I'm going to, for sake of working through it, I'm going to tell you here in a second. If you want, you can pause and try and figure out what the relationship between these two functions are. But the function relationship here is that g of x, if I take the derivative of it, I get f of x. So in other words, g prime of x is equal to f of x. Double check that for yourself. Take the derivative of this expression. If you do some use substitution, you'll see that they're related more or less like this. Let's prove exactly what that is, because there is going to be a little bit of trickiness here. So 1 over u, if we do our u substitution, u is 1 plus x squared. Du dx is equal to 2x, or I guess let's make sure there's nothing tricky here. So dx is equal to du over 2x. So that means my original function is 1 over 1 plus x squared. If I take the derivative of that, what am I doing here that's tripping me up? That's what I'm doing. I got too hasty. It's actually the other way around. It's the integral, I believe. So let's clear all this out. This is a good example of sometimes we start in the wrong direction. So I believe it should be f prime of x equals g of x. So let's check that. So negative 2 over x, 1 plus x squared, if I say u is equal to 1 plus x squared, du dx is equal to 2x. And then we do oh, I don't need to use u substitution because I'm taking derivatives. Sorry, this is happening a bit late, and I'm just getting a little turned around here. Let's pause and give me a second here, and then I'll come back once I've worked this out kind of in my head, because I'm getting all turned around. So we're going to pause here. All right, sorry about that confusion. I had to just pause here and take a minute to look through this. The derivative of g of x is equal to f of x. If we look at that, we see that when we take the derivative of this expression, we get the results of, whoops. We see that we get the results of f of x. So in other words, the derivative of g of x is f of x, so the derivative of each of these terms will give me f of x's functions. So the derivative of 1 is 0. The derivative of x minus x squared is negative 2x. The derivative of x to the 4th will be 4x cubed. The derivative of x to the 6th will be 6x to the 5th. And if we keep going, we'll see that the nth term should be 0, 2, 4, 6. So we see that these increase by their alternating series, so negative 1 to the n. And this is n times 2, 2n. And then the x is 2n minus 1. Is that right? The first, sorry, 2n plus 1. Negative 1 to the n, 2n, 1, 2, 3. So 1, 2n plus 1, 2, yeah. So this is our nth term. So this is the first example, is just if you have two functions, how are they related? And then just performing the same operation that you did to get the functions, performing that on each term in the series. So here's a second example from a past AP exam. So they give us, let f of x be equal to ln of 1 plus x cubed. And they tell us the Maclaurin series for ln of 1 plus x is x minus x squared plus x cubed minus x to the 4th, yada, yada, yada. And this is our nth term. So use this series to write the first 4 non-zero terms and the general term of the Maclaurin series for f. So what we need to do here is basically figure out how are these two expressions related to each other? Because if I know that, then I can figure out, what to change in my expression over here. And if we look, they're completely identical, but instead of x, I replace it with x cubed. So in other words, I'm going to write this so you can kind of see, because it looks a little hand-wavy, but let's call g equals ln g of, let me write this. G of a is equal to ln of 1 plus a. And let's call it b actually, so we don't confuse it with the a being the 8th term. So we have g of b. Let me rewrite this all nice and clean. Sorry, I'm trying to make sure it's easy for you to follow the logic here. G of b is equal to ln of 1 plus b. And I'm just using b, so it's a different variable. There's nothing special about it. It is still a variable. It's just like x, but instead of x, I'm writing b. Now, f of x is also the same as g of x cubed. Because if we imagine go up here and in place of the b, we just replaced it with x cubed. So that means that we get ln of 1 plus x cubed. And that matches f of x. So in other words, all that we've done is everywhere there was an x, we replaced it with x cubed. That's how these two functions are related. F of x is equal to g of x cubed. This is that key realization. If you can see how these are equal, then the next part becomes easy. Because that means if all that we're doing is plugging in x cubed into our function, that means when our function g of x is equal to x minus x squared, let's call it b, let's go back to b, g of b is equal to b squared over 2 plus b cubed over 3 minus b to the 4th over 4. Well, we know that f of x is equal to g of x cubed, which is equal to x cubed minus x cubed squared over 2 plus x cubed 3 over 3 minus x cubed 4 over 4 plus dot, 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 dot. And then this nth term will be negative 1 to the n plus 1. That doesn't change. But then just instead of x, I have x cubed to the n over n. And that's, another example. If we know how these two functions are related, f of x and g of b, then I can easily modify the series that was given to me, this series, into the other terms. So these are the first non-zero terms, first 4 non-zero terms, and then this is the nth term. So all that we did was anywhere there was an x, we replaced it with an x cubed. So as you go forward, let me know if you have questions, but that's the idea behind how we can work with series, power series, using kind of all the tricks we've learned so far.